Okay, this is David Zierler, Director of the Caltech Heritage Project. It's Monday, January 10th, 2022. I am delighted to be here with Dr. Frank Verstraete. Frank, it's great to be with you. Thank you for joining me today.
Thank you very much. It's a great pleasure to help you with this great initiative.
Frank, to start, would you tell me your current title and institutional affiliation?
Yes, so I'm a professor of theoretical physics at the University of Ghent in Belgium.
And what's your field? What are you currently working on, and what's the general area of physics that you specialize in?
Yes, so I work in the field of quantum many-body physics, especially trying to use ideas from quantum information theory and entanglement theory to uncover some of the most basic structures in many-body systems. So if you look at the history of physics, the central problem in theoretical physics since, let's say, the 20s has been exactly this many-body problem. What happens if you put many particles together? So the Schrödinger equations, the equations of motion of many particles are understood, but it's just too complicated to calculate. So the history of physics, of theoretical physics, to a large extent, has been to find efficient approximations of these equations of motion for many-body systems. And one of the great visionary insights of John Preskill was to see basically that ideas from quantum information theory, especially entanglement theory, could really help in elucidating some central problems there. And I have actually been working on this since I met John.
Frank, is it more that you use quantum many-body physics to inform questions about quantum information theory, or does it actually work the other way around?
It actually works the other way around. So I think if you look at the field of quantum information, it has exploded in recent years in terms of trying to understand, to actually build quantum computers. But if there is one single direction in which quantum information has already had a huge impact in physics, it is actually in the field of quantum many-body physics. And again, there's only one person that can be credited there with seeing this long before anybody else, and that's John. He was saying this to everybody that worked there. This is the direction to go, and many of my colleagues that became very successful have kind of also jumped in these same directions. So this is, from my point of view, the most tangible result from this whole field of quantum information at the current day. So it's impossible to think anymore of any field in theoretical physics where these ideas of entanglement, these ideas of quantum circuits has actually not permeated. So it's really in all fields, whether it's high energy physics, quantum chemistry, condensed matter physics, statistical physics. People are rediscovering and actually kind of getting a much better insight into the complicated structures of these problems by using these tools, this new language of quantum information theory that has been kind of developed to a large extent actually by people working at Caltech.
Frank, as a theorist, where in the world of observation or experimentation is there data that's most useful for the questions that you're after?
Yeah, that's a very complicated question because I'm very far off from actual experiments. So, quantum information theory has certainly inspired a lot the field of quantum optics, and especially the field of atomic physics, in which people like Ketterle in MIT or Emmanuel Bloch in Max Planck and many other groups actually in the world are trying to manipulate cold atoms to create highly entangled states of matter. Actually, at Caltech, there is also, I forgot her name, but okay, there's many people all over the world that actually are using lots of these ideas that were developed in these more theoretical approaches. So I remember, for example, that when I was at Caltech, John Preskill invited Matthew Hastings to give a talk on Lieb Robinson bounds. Okay, Lieb Robinson bounds at that time was something very exotic. Nobody had ever heard of this. And during his talk, we started seeing all kind of connections with problems in quantum information theory. And like 10 years later, this is one of these central concepts that people have actually implemented in experiments. We understand many, many new things because of this. And this all came of some discussions after a beautiful talk of Matthew Hastings at Caltech.
Now, it's always interesting asking both theorists and experimentalists this question. For you, do we yet have a quantum computer? And if not, what will it take to get there?
Well, from my point of view, a quantum computer will only be there if you have a fault-tolerant quantum computer. And this has certainly been of the major interests and focuses of John Preskill for a long time, that indeed you want to build a scalable quantum computer, you need fault tolerance. Actually, there's quite a nice anecdote with this. John Preskill is the most likable person that I know, but I got him angry once. And this was exactly when we were having a dinner or something, and I like to provoke. At that time, I was still I liked very much to provoke a bit. And I was trying to provoke John Preskill by saying that, well, this fault tolerance and all this, why are you working on this kind of thing? Because it's an engineering problem. We know that it's in principle possible. Now it's for the engineers to actually do this. I said, this is not really kind of physics. You're supposed to work on really deep problems. And John Preskill really got kind of angry. He said, no, this is actually really interesting physics and so forth. And of course he was right. Okay, of course he was right. But it's I still remember vividly that this he didn't like at all to be called an engineer.
Frank, this is as much a cultural question as it is a scientific question. In the United States, quantum computing is often thought of as something like a horse race. Who will get there first? Is there a similar phenomenon in Europe?
Well, certainly, I think the development of quantum computing has run in a very parallel way, both in Europe and the US. I think if you look at the very first realizations of quantum computers, I'm thinking about ion traps. Like the theoretical proposals actually came out of European scientists, Peter Zierler, Ignacio Schirach, these kind of people, and then actually this was immediately implemented by people in Boulder. So I think it has always been so these developments have always run very much in parallel, and I think, as far as I understand, the jury is still completely out what technology will actually win, in the sense that it's clear that we will be able to make machines with a few hundred qubits in the coming years. But maybe this is not enough. Maybe we need millions of qubits. And many of these technologies that are pursued these days are maybe not scalable. So I'm personally not convinced that, for example, ion traps or ion trap quantum computers are actually scalable to 1 million qubits. The same for superconducting qubits. There's lots of technological problems that come into play when you kind of try to scale these things up. And my feeling is that I don't really understand the sudden huge investments that are being done in this whole field. Okay, I don't see any huge leap in knowledge or any huge leap in technological discoveries that justifies the humongous investments that are being done now as to 10 years ago. So from my point of view, I think we are still very far from this scalable, fault-tolerant quantum computer. So what is pretty odd in some sense is that I started working on quantum information theory around 98, 99. And I still remember very well that when I was speaking to experimentalists, but also the real experts in the field, they always said, well, in 10 years, we will have a scalable quantum computer. And then you kind of go 10 years later and they say, in 10 years, we will have a scalable quantum computer. Now we are again, like more than 10 years later, and it's again the same. It's always this 10-year time frame seems to be like a constant of motion in this whole field of quantum information, which might actually look a bit depressing. But on the other hand, this is because somehow this is only if you look at the premise of actually building quantum computers. What is beyond any doubt is that this whole field of quantum information has led to a completely new way of looking at physics. And that kind of goes back to what I was saying before, that the most tangible results or consequence of the most tangible kind of results that really came out of the field of quantum computing is that it allows us to kind of reformulate and look at quantum physics and quantum many-body physics in a completely different way. And from my point of view, this alone already justifies this humongous interest in the field. And it's a bit odd that this aspect is not is typically not stressed too much, because of course it doesn't sound that good for funding reasons or for other reasons. I'm not so sure, but I think this is certainly as of now, this is the main legacy of this whole field of quantum information, and this legacy was actually pointed out or first really kind of seen in a very clear way by John Preskill in a paper that I think he wrote this in '99. Okay, there's like a paper that is very important from the historical point of view, in which he basically says, look, quantum information and quantum computing look like great, but the real impact that they will have is actually in other fields of physics.
Frank, is that to say that we really don't know yet on an existential level what quantum computers will be good for, even if we don't have any understanding of how we might actually get there?
So the way I look at the quantum computer is that it's effectively a universal lab. Okay, so there's many different labs all over the world where quantum physics experiments are being done, be it condensed matter, be it atomic physics, be it pharmaceutical companies in which they basically make chemical reactions. So there's many different disguises, quantum phenomena, or basically people are trying to understand how these processes or these chemical processes or nuclear processes work. Now, what a quantum computer in principle would be able to do is to simulate all these possible experiments in one and the same machine. Okay, so it is in many ways a universal experiment. It allows you to do basically any experiment in which quantum mechanics plays an important role. And in that respect, it would be, in the very long term, it will be a huge deal. It will allow you to, well, certainly for companies like pharmaceutical companies, for of course making new catalyzers in chemistry and for big chemistry concerns. So there's many possible applications of being able to simulate an arbitrary quantum process, and especially the chemical processes that are being done. So actually, I don't know the exact number. This is a bit difficult to figure out, but there's certainly like a very large fraction of all supercomputers in the world also simulating quantum many-body systems all the time. And these systems are actually using classical methods for simulating quantum systems, and in many cases this leads to something like exponential slowdowns. So that means that, of course, with the quantum machine, already this whole part of simulations you would be able to do them with a humongous speed up. But even somehow many other kind of applications that we have not been able to dream of that we could do, we would be able to suddenly do with quantum computers, because there are really lots of processes, lots of non-equilibrium physics problems for which we don't have an answer. We don't know what happens because we cannot simulate that. We cannot. There's a lack of methods for understanding how to deal with them. And to a large extent, actually, this is where my own research fits in. So by being in Caltech, but actually also a little bit before, and of course many years after I was still thinking about this, we were very much motivated to try to understand what can you do with a quantum computer that you cannot do with a classical computer. Where is the line? What problems are actually really hard for normal classical machines and easy for quantum computers? And what we figured out, and I was a postdoc together, for example, with Guy Vidal. I'm sure that John Preskill also kind of recommended him to be interviewed. So we were postdocs together. We were sitting in the same office, but we were really competing with each other. But this is the perfect environment, of course. We were really trying to push somehow classical algorithms, kind of new ways of understanding the quantum many-body physics from the point of view of this new language of entanglement theory. And this has allowed us to devise algorithms, classical algorithms for simulating quantum systems for which we thought that it would be impossible to do so. So it's very difficult. We still don't know the line. We still don't know exactly what is a quantum computer good for versus classical computers. But the great thing of this whole field of quantum information is that it gives you also tools to do these things better classically. It leads to a completely new way of understanding the central, I would say, the central problem in quantum physics.
Frank, perhaps to elucidate what quantum computing might be good for, when you look at classical computing, what are some of the obvious limitations for which, theoretically, quantum computing might provide answers?
Yeah, well, I would say that of course there is the obvious example of factoring. Okay, this is the problem that of course kickstarted the whole revolution of quantum computing by Peter Shor in '94, when he showed that indeed with a quantum computer you would be able to solve a problem for which it's thought that you need exponential resources to do it with classical computers. Now, what is this? Of course, this opened up a humongous interest of many people trying to figure out other algorithms that would allow you to have these exponential speedups. But this has turned out to be an extremely frustrating endeavor, I would say. So there's, from my kind of maybe subjective point of view, there has not been a single other computational problem that is relevant from the point of view of computational complexity that had the same input, that for which you have like an exponential speedup that has potentially the same impact as that factoring problem. But that is because to find problems that are amenable to the power of quantum computers, you must find a structure in these problems. There must be a very non-trivial structure, some periodicity or some group-like structure that you uncover, and then that quantum computers can exploit, because you can do Fourier transforms very efficiently. You can do certain types of operations that figure out regularities in the data in a very peculiar way. But it has turned out to be very complicated to come up with problems that are relevant, classical problems of computer science that you can mold in that type of framework. Now, but I think this is so in some sense this factoring problem seems to me like some beautiful kind of flower out there, but a very exotic thing. That's certainly not what quantum computers in practice will be used for. What quantum computers will be used for is, as I said before, is effectively simulating quantum systems, kind of trying to solve the quantum many-body problem, trying to understand how this how for example high TC superconductors work. How can we make materials that would be superconducting at room temperature? Having like, if this would be the only thing that a quantum computer would be able to do, kind of allow you to come up with a superconductor at room temperature, it would already basically justify the whole investment of trillions of dollars. Okay, because it would kind of be a complete, would change everything. This would be like an amazing thing. So in that sense, there's this enormous potential, but of course we don't know whether this will be realized.
Now, you mentioned high TC superconductivity, which the value from an applied level would be incalculable. What about more theoretical areas of physics? For example, particles that finally break the standard model, or achieving a quantum theory of gravity. Do you see a role of quantum computation in some of the larger intractable theoretical challenges in physics?
Yes, so sure. So quantum computer could be seen as some new device that a computational physicist would use, but nevertheless, this is not enough. Okay, so it's not because you can simulate something that it would be like more like a black box that this actually leads to understanding. So again, this would be extremely valuable, but on its own, this is not enough. It's not because you can certainly simulate maybe something like some problems in quantum gravity that you understand them. So in that sense, it's not entirely clear to what extent it's enough to have a quantum computer and we will solve quantum gravity. we'll have to have a theory that actually kind of explains this and allows you to understand basically these results that come out of the quantum computer. So actually, I know that you asked me. I remember a very an extremely heated discussion that I had also together with John Preskill and Das Sarma. Das Sarma is a famous professor from Maryland, and the question that the discussion was about is: have classical computers or computational physics, has computational physics ever led to a real big breakthrough in physics? In the sense, has computational physics, what is the intrinsic value of computational physics for understanding things? And again, I was provoking a little bit especially the Sarma, and John Preskill was like the moderator in this whole discussion. It completely escalated. This Sarma started shouting that, of course, computational physics is like the most important thing ever. But then it's difficult. It's actually very difficult to come up with examples of things that have been discovered because of computational physics. So it's not so clear cut. At the end, physics is about understanding things. Physics is about uncovering kind of regularities and writing down very simple explanations of very complicated phenomena. And from my point of view, this is what physics should be about. So of course, like a quantum computer or any interesting classical algorithm that simulates quantum many-body systems is very interesting, but it's only a small piece of the puzzle. What you need is actually that at the end, you need to have the theoretical understanding of what is going on as a whole. And in that sense, so many people like are currently very excited, for example, about these neural networks and this deep learning and all these new ways of trying to do physics also. And so this is to me this is still not clear at all whether we will be able to do big discoveries in physics using such a black box method. It's not at all clear that just being able to simulate things is enough to understand things.
Frank, some technical questions. First, what are tensor networks?
Yes, so tensor networks is indeed the main topic of my research. This is a way of organizing or parameterizing complicated many-body systems. Okay, so one of the central concepts in quantum physics is that there is something like a tensor product structure. Okay, if you take one particle and you take two particles and three particles, the dimension of the Hilbert space is always growing exponentially. And therefore it becomes so it means if you have like 10 qubits, you already have a Hilbert space of dimension 1000. If you have 20 qubits, it's a Hilbert space of dimension 1,000,000. And the fact that this grows so fast is one of the main reasons that quantum computing or that actually quantum physics as its own is such a difficult is difficult because you cannot parameterize, you cannot write these wave functions down anymore in any meaningful way. If you would have to write down all these coefficients for all possible amplitudes, well, it's an exponential problem. So and one of I think if there's one nice thing that came out of this whole COVID saga is that everybody understands now what exponential means.
That's great.
But so there's this exponential explosion, and the question is there? So this whole idea of tensor networks, like how we came up with this, is trying to find new ways of parameterizing or representing these complicated many-body wave functions. How is it possible to write down a wave function on, let's say, 100 qubits without having to specify all possible wave function amplitudes? And so what we do is effectively split up these big wave functions into small chunks, and then we connect these chunks to each other. And as a whole, this leads to a very efficient parameterization of your big wave function. because you connect small entities to each other. Now, the question is, why does that work? And this is exactly where this whole theory of quantum information and quantum entanglement kind of comes along. The theory of quantum entanglement, and especially things like these Lieb-Robinson bounds that I talked about before, they have allowed to understand that indeed relevant wave functions that actual matter, have lots of structure. If you take, so something, this is also some paper that I wrote that came out completely out of discussions that I had with people at Caltech, is trying to understand what are the physically relevant wave functions in the universe. So if you have this exponentially big Hilbert space, and the question is what part of that Hilbert space is actual physical, and what part of that Hilbert space can nature, or for the same amount, I can as well say, can quantum computers explore? And so there's one thing that is completely underappreciated by people that do not have a deep understanding of quantum information theory or quantum computing, is the fact that actually the size of your Hilbert space is not really exponential in the system size, but the right way of counting the size of a Hilbert space is as something doubly exponential. Now, what I mean by doubly exponential is that you would say, like, how many states can I create that are distinguishable? Okay, so like you have wave functions, but wave functions don't have to be orthogonal. Wave functions can kind of just be close to each other, but you can really distinguish them. And of course, with a quantum computer, you want to make wave functions that are close to each other, but not equal to each other, because you need this during your quantum computation. So what you can do is something like a counting. You can start counting how many different epsilon balls can I put in my huge Hilbert space. And if you do this, you can see that you can put in, or you can fill your Hilbert space with the doubly exponential. So it's an exponential of an exponential amount of different states. And now you can start do the counting. How many states can I actually create with physical processes, with processes that kind of systems that have Hamiltonians in which only 2 or 3 particles interact? And then you see that the amount of states that you could visit, or that you could ever create in any meaningful time, is only exponential in the system size. So that means that actually the whole Hilbert space is in some sense an illusion. Okay, so we have this humongous Hilbert space, but almost everything in that Hilbert space is an illusion, because you will never be able to make even a state anywhere close to most of somehow this Hilbert space. So that means that to do physics, and this is so very much a quantum information idea, that the meaningful physics happens on a very low dimensional manifold in this huge Hilbert space. And these tensor networks are a very specific realization of that say that if you kind of even go a little bit further, and you say, I'm only interested in ground states of many body wave functions, then it turns out that there's actually an efficient classical description of these relevant wave functions. And trying to understand this puzzle and actually come up with proofs like that was certainly one of my main works when I was in Caltech, and I have been kind of continuing to work on this ever since. And again, John Preskill was instrumental there to always ask the right questions. So well, maybe we come back later to the influence of John Preskill, but he was somehow the guy that always asked the right questions. He's the one that pushed us to think further, to really kind of think about questions like I just kind of explained, like what does that mean? What does, like, this illusion of Hilbert space? How do you kind of show this? So why is it that indeed this is possible to do this? And yeah, this is the best possible mentor, of course, that I could ever have had.
Frank, in the context of quantum computation, what does the term dissipation mean?
So dissipation is actually the main source of decoherence. So dissipation effectively means that you have a quantum system, and when this quantum system is not perfectly isolated, it couples to the environment. So what it actually does is that your quantum system becomes entangled with the environment. For example, it could be that some photon comes along kind of and excites some atom in your system. Okay, and then, so basically you coupled the electromagnetic field with your quantum system, and now they are entangled. And of course you don't have access to the full kind of environment, and therefore you have to, the technical term of this is you have to trace out the environment. And the result is that the evolution of your quantum system is actually not described by a unitary evolution, by a Hamiltonian evolution, but actually by something that's called the Lindblad equation. And this is what dissipation is. Dissipation is effectively entanglement of your system with the environment, but you don't have access to the environment. So therefore, you kind of have to throw it away. And this effectively leads to decoherence. This leads to the fact that you're, instead of having a nice pure state evolution, unity evolution, you start dissipating and you start creating entropy. And once there's too much entropy, this whole system will become completely useless for quantum computation.
When you worked on developing a quantum generalization of the Metropolis algorithm, is that to say that there were classical generalizations of the Metropolis algorithm?
Yes, so indeed. So the quantum Metropolis algorithm, I still remember very, very well. I started working on this indeed in Caltech in, I think, 2004. And this is by far the longest algorithm, or the longest paper, or it took the longest time to actually get it. So I was talking, I still vividly remember, with people like Andrew Childs, and we were talking, not every day, but from time to time, how would you do this? How would you actually do a quantum Metropolis algorithm? And I will kind of explain in a minute what that would mean. And we couldn't figure it out. But I kept thinking about this from 2004 till 2009, 2010, and then finally somehow we were able to crack the problem. But this is one of these problems that you have to kind of go back to that problem year after year after year, and then suddenly you see the light. So why did I think, or why do I think this quantum Metropolis algorithm is actually relevant, and what does it actually do? So if you look at classical many-body systems, okay, so these are classical particles, statistical mechanical particles. Think about cooling down some liquid, and it will kind of crystallize in some crystal structure. And the questions that people ask and solve using Metropolis algorithms, and these are classical Metropolis algorithms, is what is the equilibrium crystal structure? So I put this and this molecule together, and I cool it down. In what structure will the system kind of crystallize? What space group will be realized by that cooling down? And these turn out to be very complicated problems in classical statistical mechanics, unless you solve them with Monte Carlo algorithms, or these Metropolis algorithms. So these Metropolis algorithms are effectively doing random moves. So it's kind of using randomness to basically mimic some heat baths, but you can mimic a heat bath that would thermalize many orders of magnitudes faster than a real system. Okay? And then, so these Metropolis algorithms are so successful and actually have completely acquired a monopoly in solving problems in statistical mechanics of classical particles. So it's basically the only tool that still is used because it's so efficient and it works so well for simulating many-body classical systems. Now, the problem, if you try to do this for a quantum system, is that these quantum amplitudes will give rise to something like negative amplitudes. So there's no direct generalization possible of this Metropolis algorithm to simulate quantum systems, at least not quantum systems with the sign problem, because these are problems that for which you would need negative probabilities or complex probabilities. And of course, that doesn't exist. The probability has to be positive. So what you want to do is effectively sample eigenstates of a certain Hamiltonian. Now, people like Peter Shor, but then of course also people like Alexei Kitaev and many other people have shown that have developed a beautiful and an extremely important formalism of phase estimation. And phase estimation is effectively a way of preparing eigenstates of a certain Hamiltonian. And so this quantum Metropolis algorithm actually works by going from one eigenstate of this Hamiltonian to jump to another one, and then you compare, is the energy going up or down, and depending on this, you kind of make the jump or go back, just like classical algorithms work. But the big difference is that in the quantum case, these wave functions are very entangled. In the classical case, all the possible configurations are always product states, are always very simple states. So that's why you really need a quantum computer to be able to do this. Now, why did it take so long to devise this problem or to actually solve this problem? It's because there are many obstacles that have to be overcome in quantum mechanics that at first sight look completely unovercomable. So for example, one of the big things in quantum mechanics is something that's called the no cloning theorem. Okay, so you have a wave function. And out of that wave function, you make a new wave function, you compare the energy, and if the energy kind of goes up, you don't want to accept it. You want to go back to the original one. So how do you do something like that classically? Well, you just keep the information of the state that you came from. And if the energy goes up, well, you just go back to where you came from because you have a copy around of what you had before. But in quantum mechanics, that's impossible. There is no way of going back once you kind of did the measurement. It's incircumventable. It's irreversible. You cannot go back. But nevertheless, using some tricks, especially this whole mantra, use entanglement actually to overcome all these kind of things, we were able to indeed kind of understand how this could be done using quantum mechanics. And this is one of these problems or these lines of ideas to develop this or to understand this that came very much out of, for which you need really this whole environment, this very inspiring environment of Caltech, where you're continuously forced to think about how can I use entanglement to solve this problem. And this was when I was there, this was the time 2004 to 2006. It was like the golden age of entanglement theory. So nowadays people are a bit less concerned with this because in some sense all the low-hanging fruits have been kind of picked now. So, but at that time this was like the most inspiring and I think very, very deep kind of direction of research that all of us were very much concerned with. And also we were very much motivated to think about problems like that by John.
Well, Frank, to establish some intellectual context to build up to your time at Caltech, really first a generational question. So, for example, with John Preskill, who came from cosmology into quantum information, by the time you were in graduate school, was quantum information sufficiently mature that this was a viable field to focus on for you?
Yes, so as most people that were interested in theoretical physics, when I started graduate school, I thought, well, yeah, of course, I want to do string theory. I want to do the really tough stuff, and I want to be the new Einstein. But I had a very, very smart advisor who told me, yes, this is true and all this, but it's very, very difficult to make an impact in a field like string theory because there's just too many smart people working on it, and it's already an old field. What you have to do is to start working in this completely new field, and this is around 98, 99, start looking in this field of quantum information theory, quantum entanglement theory, and try to understand whether you can do some interesting physics there. And that was the only thing he ever told me, actually, my advisor. But that was an extremely good advice. So how do we start something like that? How do we start looking around or working yourself? Because my professor himself, he didn't know anything about quantum computing, but he told me, look, this seems to be a new field with a huge amount of potential. So what did I do? I started looking around for some lecture notes, and I stumbled on the lecture note of John Preskill. So I learned everything I know about quantum information theory from this amazing set of lecture notes that he put online in 90, I don't know exactly when they were written, but certainly when I started graduate school, they were there. And they are actually amazing. So in the sense that, so they are very different than all the other lecture notes that I have ever seen from about quantum information theory, because it's really not just quantum information, it's not just quantum computing, it's also about physics. It's really trying to understand or explain connection with physics and trying to illustrate why all these ideas are really very deep. And so as far as I understand, John Preskill has a contract that is probably already has been kind of prolonged for 25 years to publish these lecture notes in Cambridge University Press, but I'm not so sure when they will be finally published. But this is the way that my generation learned quantum physics or quantum information theory. It's really by these amazing set of lecture notes of John Preskill, in which he was basically kind of asking the right questions and also being very visionary and making connections with different fields. And that's what you want as a graduate student. No? You want to really be to be stimulated to think about connections with other things. And so at that time I was kind of lucky that I had a background that was a bit different than most physicists, because I also had done engineering. Actually, I was also an engineer, so I knew quite a bit of linear algebra. I knew like linear algebra is basically trying to understand eigenvectors, eigenvalues of matrices, but it's actually goes superficially, it looks very, very simple linear algebra, but actually it goes very deep. So many of the most complicated things in mathematics, when they are understood, is actually because in one or the other strange way, you can bring it back to some linear algebra problem. So even the problem of solving nonlinear differential equations or nonlinear sets of equations using Grabner bases and all these very complicated things, at the end, the way you solve it is by bringing this back problem to some linear algebra problem. And that's, so I was reading these lecture notes of Jean Presqu'île, and I figured out that actually my background of linear algebra would allow me to solve problems there that people had not thought about. And this is how how actually I came into contact with people in Caltech, especially also Hideo Mabuchi. I don't know whether you have had contact with Hideo Mabuchi. At that time, he was an extremely high profile and extremely young professor. I think he was maybe only 25 years old. And he was a quantum optics professor in Caltech. And he was really the big deal. He was the guy that was super fast. He spoke extremely fast also. You would talk to him, he would immediately understand what you said, and he would immediately come up with new ideas. And so now he's in Stanford. But anyway, so I got into contact with Hideo Mabuchi, who was also also very interested in these problems in quantum information. So was attending these weekly seminars. So I'm talking about my graduates when I was a graduate student in Belgium. So this Hideo invited me to come to Caltech, and there this opened my eyes completely because I was attending also these group meetings of John Presqu'île. I still remember, this was in this building, this high energy physics building. It was like a big room with all sofas around the room. What is the name again? Ritsen? No. Got the name of the high energy physics. What is the building of the high energy physicists in Caltech? Yeah, okay, I don't know, I also don't remember the name, but anyway, it was like, this was amazing, this electrical atmosphere that was there. Everybody was asking questions, everybody was pushing each other to think about problems, about error correction, about entanglement. Everybody was interested in everything, and there was like an amazing atmosphere that I had never seen anywhere else. And then somehow every year I was able to visit me, because John Presqu'île was extremely generous with inviting young physicists to just be there. Come and visit me for a month and work on some problems. So he invited people all over the world to do this. And this was, for me, this is basically how I really started thinking about interesting problems. Because of course, as a physicist, there's many physicists, or there's many people that can solve interesting problems, but there's only, the really kind of difficult thing is to come up with the interesting problems. And this was always very clear that this was the emphasis of John Presqu'île. John wanted people to work on interesting problems. And once you formulate a problem, once you understand how to formulate a problem, of course, in some sense that is solvable, many people would be able to solve it. But you first have to ask the right question. And this was, in some sense, what made Caltech so unique, that people were continuously pushed to think about the right questions. And John was the perfect catalyst in doing this. So what is pretty amazing, in all the years that I had, in the years that I was there, but also before as a graduate student, and many years later, John never ever wrote any papers with any of his postdocs or even his students. Nevertheless, he is on, of course, all the acknowledgements. He's the guy who kind of stimulated people. He's the one that, if you work on a problem, he would ask you the right questions, and it would allow you to see much further and see the relevance of actually, or other directions in which you would have to move in. So it is still, yeah, John was like an amazing figure in creating this whole atmosphere. Such that people would kind of see new things, would work on new things. So at some point, I think there was not a single professor in the field of quantum information in the US that was not at some point a postdoc with John.
Now, just to clarify the chronology, did you initially visit Caltech when you were a graduate student, or only as a postdoc?
No, I visited as a graduate student. I was there, I think, 2 or 3 times for 1 month. And then when I graduated, I applied to 2 places for a postdoc. One was Caltech, and the other one was the Max Planck Institute in Munich. Ignacio Cirac. So Ignacio Cirac is one of these giants in the field of quantum information, who has a very unique style of doing physics. So on the one hand, he is very close to experiments. On the other hand, he's very, very mathematical. So he has like two completely different things, and he basically divides his time on doing this thing. So at that time, actually in 2002, he had just become Max Planck director, and he was looking for people to work with, and I had the feeling that this was actually the right time. So this was really, Ignacio Cirac is really kind of one of these very few geniuses that is also willing to work with people, okay? Because there's of course other people that are geniuses, and I don't want to say any bad thing about this, but there's people like Alexei Kitaev who are amazing, but with whom it's very difficult to actually exchange ideas and to collaborate. Ignacio Cirac is the opposite. He would always be full of ideas, and he would discuss. And I remember it was very difficult for me to choose, because actually I applied to two places. I had two offers, so I could do a postdoc in Caltech or one in Max Planck. And then I decided, okay, let me first go to Max Planck, because Ignacio Cirac is really somebody that knows things that I have no idea about. That has like knowledge about quantum optics, but also about physics that is clear, is very important to know. And I had the feeling I would learn kind of more in some sense than in Caltech, because in Caltech there has always been an atmosphere, although people talk to each other, it's a very individualistic thing. So also the professors in Caltech, they would not really collaborate with each other, because they are too smart for that. They have to be the experts in their field, so they should not collaborate with each other. I never really understand this attitude, but that seems to be an attitude that is not just unique to Caltech, but to all the kind of top universities in the US, that as a professor you have to be kind of on top of your own field and not kind of collaborate too much with your colleagues. So it's a much more individualistic thing, and it's a great place to be if you already have exactly in mind what you want to work on. And this is what happened. So I did a postdoc for 2 years in Max Planck, where I started working on these tensor networks by coincidence, actually. And then after 2 years, I moved to Caltech, where basically I continued working on this, and where I kind of was able to kind of see or really kind of open up the scope of what we were doing, why these tensor networks would actually be interesting. So this was it's only at Caltech really that we realized how relevant this could be. And that's also when I was sharing an office with Geoffrey Vidal, who had also been working on these tensor networks from a completely different kind of point of view.
Frank, given that your own graduate advisor was not a specialist in this field, when you spent those extended periods of time at Caltech during your doctoral work, did John serve as sort of an unofficial thesis advisor to some extent?
Well, that would be a little bit too much, but he was, I remember him being extremely, it was the first time that somebody was genuinely interested in what I was doing, I would say. And this is, of course, enormously important, because I was really kind of a graduate student from a completely unknown university. There was my advisor was not a big shot. He didn't know anything about quantum mechanics even, or quantum computing. He was actually a control theory person that wanted me to work on quantum control. And so then come to Caltech and be able to talk with somehow this person from whom I learned everything, because everything I knew about quantum information was basically from his lecture notes, was of course a complete eye-opening experience. And then to see that this person was genuinely interested in what's doing, and also pushing me to kind of go further. Yeah, in some sense, I could of course say that he was actually much more important than my advisor. Yes, but of course to say that he was actually my advisor and giving me problems, that's also not true. But without John, I would of course not have been in this field at all. In some sense, I would not have been able to ask the right questions to kind of go in the right direction, because that's what Caltech kind of taught me during my graduate studies, no? Like kind of coming up with interesting questions.
Frank, what were your initial impressions both of Caltech and IQI when you first arrived as a graduate student? What was that like for you?
Well, it sounds maybe very strange, but if I think about Caltech back, and I think this was my very first impression of Caltech, is that it smells so well. There were these flowers. I forgot exactly what flowers they were, but every time I had to walk to my office, I had to walk past some beautiful flowers that smelled so well. And this is like what I have to think about. For me, this whole place of Caltech is like this dream place. It's like this very elusive, small island in which you can completely focus on what you're interested in. There's nothing else. Everybody there is completely focused on doing research, and you don't have to be embarrassed to claim that actually even at night or after having beers that you're still talking about physics. This is like, for people like me, this was a dream, of course, because, well, at home in Belgium, of course, you're kind of looked upon as a complete nerd if you would do this. No, if you kind of you're in a bar and still talking about physics. But there, now, this was the norm. This was possible. Now, of course, this is the thing in a very general thing. But IQI was like the reason that IQI worked so phenomenally well was this one invention of John that everybody in the world tried to replicate, and nobody really managed to do this. These were these group meetings. I don't know if you must have heard of these weekly group meetings. I think it was like Wednesday evenings at 5 p.m. And this was like the time that everybody, all the postdocs, the PhD students, they would come together in one big room, and John would basically ask, everybody would have to say in 2 minutes what they had done. What have you done, or what are you working on, and what kind of problems are you interested in? And in retrospect, at first I didn't get why this was so relevant. But in retrospect, this was so ingenious of John, because what you see is really how ideas mature. So everybody is every week basically telling what they have been working on, and you see ideas evolve. You see basically how the different ideas that people are working on, they start somewhere, they end up in a completely different place, but much more interesting even than where they started from. And to kind of understand how this research works is like one of the most kind of interesting and amazing things that you can see as a researcher, that trying to understand indeed this process, this creative process, how does that work? And this was what happened at these meetings. So everybody was talking for a few minutes, went to the blackboard and drawing pictures and explaining. And John would always ask the right questions. So this was unbelievable. So John was always sitting in his one chair. So this was one chair that nobody else could sit in, and he would be there and take notes. So he had like a notebook, and he would always take notes of everything that was said. And then after people were kind of, after 2-3 minutes, they were kind of finished speaking, he would ask a question, and it would always be exactly kind of a question that the speaker would not immediately know the answer of, but let the speaker really kind of thinking about completely new avenues. So this was the magic of these meetings. So we all loved this. No? We were there, and John was sitting there. So many people, everybody that ever was in Caltech has tried to replicate this thing. Okay, everybody has tried to replicate this thing in their own groups. I also tried, of course, and I still try. Now, why, in my case, well, it doesn't work at all, and in any way as well as what John did. So why does it not work like that? It's really because John was this person that everybody looked up to. So my students, they all think I'm kind of, I'm always bothering them with questions, and I'm actually, well, they don't say I'm stupid, but I like to always engage them, and they don't take my questions very seriously. But John was this completely different figure. Everybody had uttermost respect for him. And so when he said something, everybody was always immediately silent. And he was, I don't know exactly how it went, but this was like an amazing experience. Of course, this was very stressful for like the new people, for the new PhD students. They would have to tell there on the spot what they had been doing. And then of course, the other people, the other students and postdocs, they would also ask questions, and they would bombard you with questions. If you would say something wrong, you would have known it. Okay, so this was like not the place to, so this certainly gave a very kind of you, what it forced people also to do is to make sure that by Wednesday night, you had some interesting things to say, no? Because this was like John was sitting there, and you don't want to disappoint John in his kind of big chair sitting in the in this meeting. So this was like the focal point or the focal moment of the week for everybody. Okay, because we would learn basically what everybody else was working on. We kind of would be bombarded with new ideas, and we would see how this giant in physics, John Preskill, would actually ask questions and give ideas of how to kind of advance this and actually connect different people with each other. That was his role. That's what he saw as his role. He saw his role as synthesizing what other people did. And this is basically I don't know anybody else, not any single other physicist that is able to do it in such a simple way. So when you explain what you're working on to John, after a few minutes, you will kind of, the discussion might end, or it might take a few hours, but what will always happen is that you understand the problem much better than before you talk to John. So John has this amazing quality that you can explain him anything, that doesn't matter what, you explain him in a clear term what you're working on, and after a few minutes you will understand the problem much better yourself. And this is, I don't know any other physicist with that with that vision, or with that kind of generosity also, because at the end, of course, this is being extremely generous. No, he has always been extremely generous with his thoughts, with his time, with connecting people, with everything. Okay, also I think like writing reference letters. Okay, all these people that got positions is because John generally took the time to explain what they did and why he thinks that these people do interesting things, and so he John is certainly like one of these central figures that are needed for a field to basically be happy. Okay, so people like John, they form some connection. They connect different people that might be competing to each other, but because of somehow his attitude, now we don't see each other as competitors. We actually see each other as colleagues that kind of work together. So John is one of these central figures in the field of quantum information that makes this field such a nice field to work in. It's difficult to exactly explain why this is, but it is without a doubt that he is like this big giant figure that towers out about everything and makes sure that the field works.
Frank, when you initially came to Caltech, organizationally, was IQI already in existence, or was it essentially just John at that point?
I think IQI was just there. I still remember I have a hat of IQI. And another person, of course, that was very important in IQI was the secretary. Her name is Anne Harvey. I don't know if you kind of have heard of her, but she was extremely nice. So like people like me, I came there. At that point, actually, I had a wife and 3 children. So 3 very small children. They were like 1, 2, and 3 years old. So of course I was completely lost. We had no idea what to do. But then his secretary, Anne Harvey, she was extremely efficient and nice in organizing things and helping around and getting stuff for us. And this was like, so from the organizational point of view, I think she was indeed the secretary from IQI. So IQI must have been around then. In 2004, certainly from 2004 to 2006, this must have been IQI. But who else? But there were many professors already involved. No? There were like people like Jeff Kimball. Of course, Hideo Mabuchi was there. I don't think anybody of condensed matter was already part of this. There were some computer scientists. Oh, of course, Alexei Kitaev was there. But Alexei Kitaev always remained some elusive figure. He from time to time he popped up in some seminar or something, but most of the time we didn't see him. He was thinking too deep on different problems. And there's this amazing anecdotes also of Alexei Kitaev. Alexei Kitaev is of course also the person that. So John Preskill is the one who kind of saw that Alexei was a genius. Nobody else had seen this, but John saw this very clearly and said, he has to be at Caltech. And there's these amazing anecdotes of people that were so excited because Alexei had asked them to come his office. So I think it was Norbert Schuch, and he was asked to go to the office of Alexei Kitaev, and he thought, well, Alexei Kitaev is probably interested in my recent paper. And then this Norbert Schuch comes into the office, Alexei Kitaev, and Alexei Kitaev is asking, look, I saw somehow this figure that you made in your paper. What kind of code did you use for making that figure? And it was like the only thing that he was interested in, not the physics at all, no, just the practical thing of how to make such a figure. But this is like the way Alexei Kitaev was. He was like this elusive figure in IQI, but we all knew he was a genius, but we did not really have contact with him.
Frank, when you accepted the offer at Max Planck, did you understand at some level that you would still have an opportunity to do a second postdoc at Caltech? Did that make the decision easier for you?
I don't really remember that. I certainly didn't have a lack of self-confidence. so I probably imagined that if I kind of keep on doing good work, that John would probably still hire me. But of course, this was no guarantee at all. And but from my point of view, and if I look back at the decision I made, I think it was certainly the right decision for me. So in Max Planck, I was like very privileged. I had an office exactly next to Ignatius Chirac, and I think we talked every day for something like 2-3 hours, but really every day, 3 years in a row. Every day we were kind of discussing for hours and hours in his office. And actually the other postdocs were very kind of angry at some point at me because I didn't have time for them. But that was Max Planck. And then for me, the perfect kind of jump was to go to Caltech, in which I could kind of now work and think continuously on, because now I had really kind of many more problems to work on that I would have time on to solve. Okay, and I would have a very clear vision, and I would kind of talk with John. He would kind of give me ideas. I would talk with people like Andrew Childs, with David Poulain, with many other kind of extremely interesting people, with Guy Vidal, and that would kind of completely kind of make this direction much more complete, and would form the basis for everything that I have been doing actually since then. So for me, this was actually the perfect jump. So being a postdoc in Caltech without having a clear vision of what problems you work on was actually hard. Okay, so in some sense you're continuously kind of bombarded with ideas, but nevertheless that doesn't mean that everybody had it easy. Okay, so there were certainly some postdocs that for which there was no clear line of research that must have felt very frustrated by, well, exactly also because of these Wednesday meetings. No, there's a very clear kind of hierarchy there. No, there's people that always have like these amazing results, and then there's people that struggle very, very deeply with some problems and maybe never able to solve them. So of course all of these things have also to do a lot of with luck. But nevertheless, I would say Caltech was a fantastic place if you were lucky to be good. If you were a little bit less lucky in the sense that you didn't find exactly the niche of problems that you could work on, I think it must have been a very frustrating place.
Now, as you mentioned, this was a golden era, 2004 to 2006, with low-hanging fruit. What was the low-hanging fruit at that point?
Yeah, the low-hanging fruit was that you could try to understand what entanglements or how should I formulate the low-hanging fruit? So this was the very first time that you could think about entanglements. That the language was developed to understand quantum correlations in a new way. Okay, and so if I would look at the papers that I wrote when I was in Caltech, many of those were obtained in a very quick way. So of course, if you kind of come up with a result in a week, it must be a low-hanging fruit. Okay, so that's really, you come up with a result, you write the result down, and after a week, it's already on the archive, or maybe a month. That means that from the technical point of view, it's probably not very hard, but that does not mean that it's very interesting. Okay, so I remember like a person, Yikai Liu, he came and gave a talk about some complexity, some problem about understanding the complexity of finding reduced density matrices. And then, well, you're having this talk, And after the talk, we are discussing also with John and this guy, and you immediately come up with a new problem. And basically, the week or 2 weeks after, you already have a draft of a paper in which you solved a new problem. And this is basically the complexity of one of the central problems, or the kind of characterizing the computational complexity of one of the central problems in quantum chemistry. This is called the n-representability problem. So these are these. I'm not saying that in retrospect this is a super important problem, but nevertheless, it's one of these ideas that belongs now to this canon of what is difficult, what are the kind of problems that you can solve efficiently with a quantum computer, what are the problems that you cannot solve. These were kind of these problems. The same thing with these Lieb-Robinson bounds that I talked about before. So Matthew Hastings was giving a talk about Lieb-Robinson bounds and how this could be used to understand the decay of correlations in quantum many-body systems. So this was like nobody had ever heard about this. I was sitting in the audience, and I was at that time thinking very hard about the complexity of preparing topological wave functions that exhibit something that is called topological order. This was something that Alexei Kitaev together with John had worked a lot on, and they have a beautiful paper on this. And I was trying to understand how hard is it to create states that have such topological order with a quantum computer. And you listen to this talk. This Matthew Hastings is kind of asking or kind of giving somehow ideas that fit exactly in the line of thought that I needed to solve this problem. And then basically after that talk, we sat together with Matthew Hastings, and also Sergei Bravey was joining, and we just solved the problem. Okay, we just solved the problem in basically a few hours. So now this is kind of considered, people say this is a very deep idea. Well, I don't know whether it's deep because we solved it in like a few hours, so it cannot be that deep. But it is a kind of a witness of the fact that this was the golden age. There were like these completely unexplored ideas that you just had to put the pieces of puzzle together, and suddenly you understood something that you had no clue that somehow would be that these Lieb-Robinson bounds would be relevant for understanding the complexity of preparing topological phase of matter. This is like, wow, this is something that you could never have dreamed of unless you are in this surrounded by this whole atmosphere of Caltech, in which you're always thinking about new things and new directions, and there's people coming giving talks and discussions that ensue after these talks. And so these are two examples. There's many more examples that I could give like that for problems. So that's why I think I think it was a golden age. So in that sense, I forgot who said that. I think was maybe Dirac or something that said that that in the golden age, what was it again? I forgot. So in the golden age is when third-rate physicists can make first-rate results or something like that. But I forgot the exact quote. Okay, I forgot. But there's some famous quote about this.
And Frank, just to clarify, are you saying this is the golden age retrospectively, or did it feel like the golden age in real time as you were at Caltech?
It didn't feel really special because it was just normal. It was like the normal thing that you would come up with new ideas and new problems every week or 2 weeks. This was like the modus operandi there. People, the people that were there, people like Sergei Bravey, Andrew Childs, David Poulin, Geoffrey Vidal, they would always kind of have new ideas, and in that sense we didn't feel that this was so special. It was like completely normal to us that this happened. So indeed, I don't think we realized that this was a golden age.
What kinds of collaborations did you do when you were at Caltech? Who were the key people that you were working with, and what publications came out as a result?
Strangely enough, I don't think I actually have. When I was at Caltech, I wrote very, very few papers with people at Caltech. Also, and certainly not the only one with that profile. I think we discussed a lot with each other, but that doesn't mean that we wrote papers together. So we all had our own field, and we all had our own vision of what problems we were interested in. And But for one of the other strange reasons, we didn't write papers together. I don't quite understand why. I never really understood why, but this worked, and it worked very well. Okay, people had all their kind of own niche. Like I was sitting in the office with Guy Vidal. We were working basically on tensor networks, both of us, but we had like our different approaches, and we didn't write a single paper together. Although we knew very well what we were doing, and I was very much inspired by discussing with Guy, and he was also very much inspired by what I was doing. So in that sense, there must have been some atmosphere that indeed we were maybe some competitors in one or the other way. I don't know. It's now maybe in retrospect. It's only because you're asking not that I'm thinking about this. I never thought about this before, but there must have been something that we all liked each other very much, but nevertheless we were in some sense also competitors. No, there was like a very healthy competition there of being the best.
What did the competition look like? I mean, how do you quantify or define being the best? Is there a race? Is there a depth of understanding? How do you measure such things?
Yes, a very, very good question. You feel it. It's one of these things. So one of the strange things in physics is that, and especially in doing research, and certainly research in some novel direction and new directions that people have never worked on before, is that your gut feeling is so important, like your intuition. You don't really understand why, but you just feel that this is the right direction and you just go there. So in the same way, if you discuss with somebody, just feel this guy has, or this woman has a very deep understanding of this thing, no? That they really see things that nobody else sees. This guy is really able to solve problems that nobody else can solve. And I think that's how you quickly see this. But of course, this might also be completely misleading. I remember, for example, when I was a postdoc, Sergei Bravé was also a postdoc there, and I remember thinking, Sergei is such a smart guy. Why is he working on these problems that to me looked completely uninteresting? But in retrospect, actually, these problems were extremely interesting. No? So like 10 years later, everybody was working on this magic state distillation and all these kind of things. So of course, we make lots of mistakes. It's like you can be completely wrong. But nevertheless, so the thing is, it's not that one was the best or the other. We were all very good, I think. I'm now not speaking, I'm not speaking about myself. This sounds maybe, maybe a bit pretentious to say this, but I think we were all kind of aware that we were good and we were doing good science. And it's not that one was better than the other one. No, we had our own approaches, and probably that's why we didn't really collaborate together, because we didn't want to. I don't know. Actually, I don't know. But this was an amazing. There was certainly an amazing atmosphere there.
And was your feeling that IQI was an island? How well integrated was it within Caltech? Mathematicians, condensed matter physicists, who else was sort of in and out of the IQI world at Caltech?
It was a bit of an island. So there was certainly some discussion with computer scientists that were interested in quantum complexity theory, but they were always, there was like not the core of IQI were certainly the postdocs. So the postdocs were in the same big office, so there were like some different, we were all together there and we were all the time together and discussing. And there were basically everybody was a physicist and we were really on an island. So what was, for us, it didn't matter because we had extremely interesting discussions. But what I remember is that the PhD students were quite frustrated because they were actually in this high energy physics. I think it was called Lauritsen, the building, the name that I looked for before. So Lauritsen is like this high energy building. And actually all the PhD students of John and of all the professors, they were there. And they felt always a bit frustrated that they were not really in the middle of the action of this office with all these postdocs that were discussing all the time and kind of writing on the blackboard. And so this must have been, this was not so ideal actually for PhD students.
What did you learn at Caltech, both scientifically and just working in that environment, that was so important for your next opportunity when it was time to move on from Caltech?
Yeah, of course, the most let's say that I think the most important thing that I learned in Caltech is probably the real joy of doing theoretical physics, the luxury, the feeling of this amazing luxury of being able to be there to do, to try to think deep and solve problems, and being appreciated in doing this, not feeling like no, really kind of generally feeling that people appreciate what you're doing. I think this is like certainly as a student or as a young postdoc, this is like, of course, the most important thing you want to get. Now you want to see that actually very, very smart people like John and of course all the other kind of professors there are generally kind of supporting you and I want you to succeed. No, they really want you to do interesting stuff, and they don't judge you. They don't judge that you should kind of get results quick or not. They leave you free, but they continuously bombard you with interesting ideas, and that whole atmosphere is pretty unique. I've never seen this anywhere else than in IQI, actually.
What kind of opportunities did you have following Caltech?
Yes, so in the second year when I was in Caltech, I started applying for jobs in various places, lots of them in the US, also in Europe. Actually, I also applied to a hedge fund because, of course, I didn't know I would get kind of an offer at university, and for one reason I was very lucky. I got like bombarded. So this is the thing: once you get one offer, people know this, and you get offers everywhere. So I had like the luxury of the choice, and but then decided together with my wife, because I had a wife and 3 children, we decided actually that we would go back to Europe. Not that we didn't like it in the US. I think the US is an amazing place where you immediately feel welcome. But nevertheless, we at that time thought it was a bit too materialistic. That it did not completely resonate with the way we were kind of raised, in the sense that being rich in the US allows you to do things that you cannot do if you're not rich, or that it's all about that there's so much kind of let's say that the differences between rich and poor people are so huge. Also that there's some strange dynamics going on in the US that we felt like let's go back to Europe, in which we will be able to raise our children in a much more kind of normal climate that is a bit less materialistic. I remember stories of colleagues that indeed stayed in the US for a few years, then came back to Europe, and these children could not adopt anymore in Europe. They basically run away back to the US because somehow this was like impossible to adopt, and we didn't quite understand this. We were a bit puzzled, and that's why we decided to go back to Europe. Of course, also I got an extremely interesting offer from the University of Vienna. I would kind of be from being a postdoc, I would immediately be a full professor with a very nice salary and with a chair and with postdocs. So of course this was also very nice. Vienna was an amazing city with a humongous kind of history of doing research on fundamental research on physics, on quantum physics. There were people like Zierler. They were very interesting. There was like a very interesting atmosphere there for doing things, and I just accepted that offer. But I think if I would not have had a family and not having children, I would have stayed in the US for sure.
When it was time to start thinking about building your own group, essentially from scratch, in what ways did IQI and even John Preskill serve as a model for how to do it in your own department?
Well, of course, the first thing you try is to have these group meetings. but of course, that kind of works, but you can never replicate. No, you cannot do this. No, of course. So what still to nowadays, there's nothing that I value more than discussions among my students, among the postdocs. So I especially kind of built an office now here in the University of Ghent. It's one big open office in such a way that the postdocs and the PhD students are all sitting together, and there's also a big blackboard, and And anytime people are discussing, I encourage other people, even if they don't understand, even if they're new, to just sit there and listen along, such that everybody kind of has the chance to be kind of inundated with the way people discuss, the way people think. And this is of course very much inspired, or this is very much the spirit in which physics was done at IQI. Discussions, all the time discussion, challenges, like saying, no, this is stupid, you don't have to do it, you have to do it like this. And then of course then people react like a very open atmosphere, also that there's no hierarchy. Like John also would never pretend of being smarter or knowing better than the postdocs or the students. No? He would just ask questions, and he wouldn't mind being wrong or something like that. He would just ask questions and making sure that there's actually, although he was this towering figure, you didn't feel like he was much, I don't know, he was very much part of somehow the whole discussion, and you wouldn't mind also saying things that were wrong to John, in the sense that he wouldn't mind, okay, that you say something wrong. He would correct you, and he would say, no, it's probably like this. So this is the atmosphere that I try very much to replicate in my group, and I certainly have been a little bit successful in this.
Did you see the low-hanging fruit become smaller, so to speak, when you were setting up your own shop?
So, yes, for sure. I have to think now. It's a bit, of course, yes and no. Somehow I think I was very, very lucky with these tensor networks that it took a very long time before other people really started being kind of working in this field. So this really took till 2010 or something like that before really many other people started working on this. So basically I had this almost 8-year stretch of being one of the only persons in the world working on the theoretical aspects of tensor networks, actually also the numerical aspects. So for me, this golden age certainly kind of stretched all the way to something like 2010. In that sense, I was very lucky. So I have to think about the golden age of quantum computing, quantum information. Certainly, many of the problems that people are working on now are problems that people already started working on again in this time until 2010. So I think actually also in quantum computing, quantum information, I think it's not just these tensor networks. The golden age, I would say, it was something like between 2000 and 2010. This is really the people of my generation made their careers there and came up all with very original and beautiful ideas. And after that, I believe it became harder actually for new people or new students to come up with problems that had a big impact. Of course, there were still amazing results and beautiful results, but typically, I think one of the witnesses of this is that papers became much longer. So I think if you look at the average size of papers before 2010, most of the papers were like PRLs, physical review letters, like 4 pages, in which you have like an ID, a very good ID, you write it down and you go immediately jump to the next ID. Okay, so you don't spend too much time writing it down, but nevertheless, 4 pages is like this perfect format in which you can really kind of explain everything of this one great ID. Also, John has like amazing papers of 4 pages. So and 4 pages is in some sense this perfect format. If you have like one very good ID, you can condense it to 4 pages and people really read this. Okay, so it's very easy to read. But I think after 2010, papers became longer and longer. Okay, it's because they became much more technical. The papers became like much more mathematical, much more technical. The proofs became very, very long. And of course, this is also very valuable and it's very important for a field to mature. And I don't know, the golden age, it's difficult to say, is this really when lots of new ideas come, or is the golden age actually when all these many ideas are completely worked out in a beautiful general framework? You could also call this a golden age. But from my point of view, the most important thing in physics are really the original ideas. And in that sense, I think all the time before, the IQI age was the time when it happened.
Franken, for you, leaving Caltech, what were some of the big questions that you wanted to pursue next?
Yeah, it's not that I had the feeling now I have a tenured position. I have to start working on something very deep now. I want to kind of really spend my time now on a very important problem, because my experience, and this is also what I experienced in Caltech, was that actually working on relatively minor problems is very important to come up with big ideas. So I think it's very important to even work on problems that at first sight don't look very interesting, but might be just very technical. You work on them, and then only by working on small problems, you actually from time to time see big kind of ideas popping up. And I kept on doing physics like that because, well, it just worked. And of course I had this, so I had laid this foundation of these tensor networks, both in Max Planck and then also at Caltech. And to me, it was clear that this was like an amazing opportunity, that these tensor networks are like a new type of field that seems to give a new language for tackling some of the hardest problems in quantum many-body physics or in theoretical physics. And actually, still, as of today, we are really in this process of reformulating some of these or trying to understand many ideas like in conformal field theory, but also in topological phases of matter in the language of these tensor networks, and they really keep on giving non-trivial insights. So it is in that sense I have been, of course, extremely lucky and fortunate that I just was lucky to be there on the right time, the right place, having kind of had the right mentors to ask the right questions, and then in some sense everything rolls on its own. You of course you have to keep on working very hard, but the world is very unfair. Once you're kind of on a roll, once you understand things that very few other people understand, you keep on understand more and more and more things that nobody understands, and you keep on having somehow a head start on all new projects you start, and that's how the academic world works, and it's very unfair, and it's very nice if you're one of the lucky ones for which this happens, and it's the opposite if you're not lucky like that. No, but certainly, again, I think to remain being lucky, the important thing is there to continuously be interested in other results and trying to kind of understand other problems that people have and trying to reformulate it in your language, to continuously reach out. And this was the one thing that was extremely crucial and central in this whole IQI, is that we were continuously bombarded. John invited all kind of people that, even if they didn't work on quantum information or entanglement theory, they were kind of giving talks about problems that were very relevant for kind of opening or broadening our horizons, and this has led to somehow these many insights. So of course, so maybe John was not my advisor or something like that, but he was kind of much more important than my advisor. He's the one who taught me about both the joy of doing physics, but especially also kind of the person who kind of who made me think about what kind of physics do I want to do, what kind of problems do I want to pursue, how do I come up with new and original ideas. This is what I learned at IQI, and this is of course the most important thing as a researcher for the rest of your life, to be able to kind of come up with interesting problems.
Now, from the outside looking in, what did you take away as the significance when IQI became IQIM? What did the M mean for the field?
Actually, what is the M standing for even? Matter?
Yeah.
Is matter, yes. No, this was very much, this was exactly very much in the direction of the problems that we were working on. Like these tensor networks were exactly showing that this whole idea of entanglement theory was relevant also for kind of problems in condensed matter, in many body physics. So of course, this was this is one of the this was very nice. Of course, myself, I didn't didn't pay any attention to this name change. That remained IQI. It's like you've beaten IQI. It's IQI for always. But of course, this whole idea of the fact that entanglement theory is relevant for these different fields, especially for condensed matter and also atomic physics. As I said in the beginning, is probably, as of now, the most important legacy of the whole field of quantum information.
As the field has developed and similar centers of quantum information have grown throughout the world, where do you see IQI in the development in this global effort to expand the field?
Well, this is still the place all the best people want to go to. Okay, so if you're a postdoc and you're doing quantum information, then Caltech is still the place you want to be. It is really the center. It is the place with the biggest history, but also with where the best postdocs are. So it has kind of remained that amazing aura that if you want to become a professor, you have to be a postdoc. You must have been a postdoc with John Preskill. And this is, of course, not a coincidence, no? Because it is indeed this extremely inspiring place. So certainly in the field of quantum information theory, there's no place like it. There is nothing that can even compare to it. So there's, of course, like places like MIT where Peter Schoror, and then there's places like Berkeley with Vazirani, and but these places are much more specialized and let's say are in the history of the development of quantum information have had, I think, a bit of a less an impact because they didn't have this completely open and welcoming attitude to different communities kind of coming together. And this has been always one of the central mantras of John, that he wanted indeed the condensed matter physicists to be part of it. He wanted the atomic physicists to be part of it. He wanted to kind of join all these communities because he realized that this whole language of the high energy physics, of course, the it from qubit kind of people, he realized that quantum information is actually a perfect new language for doing quantum many body physics. And in that sense, it has always remained a very special place, because Caltech is not about one person. It's really about the whole community. And the other places are more, you go there because you want to work with one person or something like that. No, Caltech, you go there because that's where things happen.
What you're saying then, of course, is that from the beginning, when John is after the most fundamental questions, it requires all of the people, all of the different kinds of specialists to contribute to those questions.
That's true, but nevertheless, I don't think that John made, of course, this is my own feeling, but I could be completely wrong. But my feeling is that John did not really kind of choose postdocs because they were kind of coming from certain fields. He just chose people because he thought, I believe in these people. I believe that these people have some very original kind of take on problems and they will do interesting work. And that's the way it went, I think. So it's not. I might be wrong. I'm sure you will ask me, John. But he was just amazing in attracting the right people that were all very independent people and could kind of, he put these people together and the magic kind of came out of it. It came out of the discussions. This is what I remember from Caltech. Oh, every day I was so happy to go to the office, to stand in front of the blackboard and discussing with people and saying that they were wrong and hearing that I was wrong and striving to solve somehow, solve anything, like everything that came up in our minds. And of course we are very lucky to be there in the golden age. That is pure luck.
Frank, two last questions looking to the future. One, how do we understand developments in the field? Looking back at when you initially got to Caltech to here we are in 2022, how do we measure progress? What does it look like to you?
That's a very interesting question. So that is again difficult to measure. So of course you could try to measure progress in the field in the sense that, okay, there's so many more papers and there's so many more people working on it and there's so many more citations and all this. But this is certainly not how people from the field we don't care about. We care about fundamental new ideas. And the progress. So one thing that is, I would say, is very frustrating is the complete lack of quantum algorithms for solving kind of interesting problems, real world problems that have nothing to do with quantum mechanics, like factoring. I think this is certainly something that, that is worrying us all as a community. We don't really talk about this too much, but it is. I don't think we fulfilled that promise. Okay, so when I started in this field of quantum computing, there was still this amazing kind of idea that with quantum computers you would be able to solve lots of problems exponentially faster than with classical computers, and that premise has never kind of been realized. So who knows? Of course, it could still kind of be realized, but that's certainly one of the things that put us with our feet back on the ground. That we have to be a little bit careful in thinking that quantum computing is like the biggest thing ever. Okay, so it is not. Okay, so it is very interesting. It's extremely interesting. It allows you to do new ways to do physics, but that doesn't mean that it revolutionizes everything. So for me, this is certainly has been a little bit of a this has certainly been a reason that I have been less that my work has more and more evolved towards the direction of understanding quantum many-body physics, as opposed to working on quantum information problems or quantum computing problems that are more and more becoming engineering problems. So of course, so what are the big issues? What is the big problem? And it's an extremely interesting technological problem, is how do you make a quantum computer? How do you make something fault tolerant? And I think that, again, that the focal point in the world of research on that topic is, again, Caltech. Okay, especially now with this whole Amazon kind of cluster that is built there, with that is completely focused on this. This is indeed somehow, if a quantum computer has to be built, it has to be a fault tolerant quantum computer. And this is now a technological problem. It's an engineering problem, and that's why you need new means or new methods for doing that. And that's exactly what Amazon can provide. Now, I don't know exactly what budgets they have, but it's something that is indeed not as much in the spirit anymore of what I kind of remember of IQI. IQI was really about fundamental ideas, was about fundamental, very original new ideas. What the field needs now is not fundamental new ideas, it's just very good engineers that get things done and get things to scale up. And that's what, of course, is being done. So in some sense, the golden age for experimentalists is probably, I'm not so sure if it's here already or if it will be there in a few years. That's not entirely clear to me, because I'm not really I'm not very familiar with current state, the state of the art experiments. But that's certainly the way this whole field of quantum information is evolving. So this is one aspect of it. The other aspect is that, as I said, that papers are getting longer and longer. Mathematics ideas that are needed to make progress are getting deeper and deeper. And in that sense, this is also a very interesting development. Also, for example, at Caltech, there is this prime example of Thomas Wiedig, who kind of obtained like revolutionary new insights into some of the biggest open problems in mathematics using quantum information tools. So this is another direction in which the field is evolving. It's really kind of evolving in this language has matured in such a way that it allows you now to solve deep problems in mathematics. Of course, this is from my point of view equally valuable than actually the problem of building a quantum computer. And so this is also kind of a very valuable thing. And the third kind of real pillar of research that I find extremely interesting is, of course, trying to understand entanglement in many-body physics. This is not per se quantum information, but it's clear that every, like at all top universities in the world, whether it be MIT, Harvard, whatever, so people are all kind of very much reading the lecture notes of John Preskill, whether you kind of do high energy physics or you do quantum chemistry or whatever problem that has to do with something like the quantum any-body problem. People have to know about entanglement theory. People have to understand this, because without this, you cannot follow any of the current kind of literature or the current kind of the state-of-the-art research anymore. So in that sense, research has completely changed. The language in which research is being done, you cannot follow it anymore if you don't have any background in quantum information. And I think the credit for that is really almost uniquely has to be given to John. John is the one who understood this. John is the one who pushed his students and especially his postdocs to kind of work on these problems, to explore connections between physics and entanglement theory, physics and quantum information theory. And he did this starting in 99, 2000, and all the way somehow till now. And this is, of course, I think, well, it's certainly like a big part of his legacy, that he gave us kind of problems to work on for the rest of our lives, basically.
And finally, Frank, last question. This has been a theme that's permeated our discussion. In thinking about the upcoming 25th anniversary of IQI, IQIM, and John's directorship of it, how do you understand his legacy in historical terms, both for you personally, for the field, in his capacity as a mentor, and perhaps most importantly, in his capacity as a visionary?
Yes, well, I think I will have to repeat myself here in saying that John is the one who understood the relevance of quantum information long before anybody else, in the sense that he understood that this gives you a new language for doing physics, for solving the big open problems in physics. And he really pushed all his students and postdocs to explore this. And he, yeah, I think from my point of view, maybe this is of course very subjective, but from my point of view, this alone makes him great. But he was much more than that. He was always extremely passionate in sharing ideas. He was extremely how to say this. He was the one who let us think further, who made sure that we were not just happy with the latest result, that once we had a result that we actually should kind of explore now, we should go much deeper and much further. So he's the one who created this whole fantastic atmosphere in which we kind of competed, but on the other hand, all worked together and were pushing each other, such that we would basically, we would be able to shine during his kind of group meetings. It's difficult to say, but John had like an amazing influence on all of us. He made sure that we were, I have said this many times, but he made sure that we had joy in doing physics. And I think this is one of the best. I have tried to kind of give this also to my students by mimicking how John does that. It's really kind of seeing what kind of questions do I ask my people, or what kind of questions do I have to engage people in, such that they will discover new things themselves. So I'm sure that many of the things that John was asking, you already knew the answers of, but nevertheless, he would not tell the answer. He wanted us to discover it, such that we would also come up with something new in the meanwhile. And this is, so he was always extremely happy to share all his ideas, which there's nothing more that you can wish from an advisor than that.
Well, Frank, on that note, this has been a tremendous pleasure spending this time with you, and what a wonderful addition as we work towards 2025 and the anniversary. I'd like to thank you so much.
No, I'm